represents for spacecraft designer an effort task to be boldly mastered and refined. This should include how to foster for more efficient and durable technology. We are grateful that today we are going to learn from the authoritative experts in this very subject. Thank you to Lapan and to TELKOMSAT for supporting this event by allowing their power system designers to share their knowledge and their real experience in this very important field. After all, this workshop is just one form of collaboration and networking of professional engineers and engineering students. It should be more than lovely should this chain of networking between the authors and institution be ever strengthened in the future. Please allow me in this occasion to express my sincere gratitude to the speakers, moderators, steering and organizing committees, 8 BRIN organizations, and the Laboratory of Satcom Radar Nanosat Division of Telkom University for their continuing effort to make this workshop happening. Last but not least, our high appreciation should go to the audience for this workshop, without whom this event becomes meaningless. Please stay tuned to our future technical workshops featuring aerospace electronics, geoscience, and remote sensing technologies. You always are welcome to adhere to GRSS societies of the IEEE as a member or just an association to it. Finally, we wish you a full enjoyment of this workshop. Looking forward, of course, by Allah permit, to have the opportunity to have a physical workshop in the future, to see the compatriots, the beauty of the nature, the culture, and why not, the culinaries. Thank you very much and have a pleasant workshop. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you to Mr. Arvin for the welcoming speech. The second welcoming speech will be given by Dr. Adia Pramudita STMT, a supervisor of Satcom Radar Laboratory at Telkom University, which will be represented by Mr. Edward STMT. Please welcome Mr. Edward. To the Honorable Mr. Edward, time is yours.
Thank you. Am I audible?
Yes, Mr. Edward.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. The Honorable Dr. Arifin Nugroho as the IEEE, IES, and GRSS Indonesia Joint Chapter, and the Honorable keynote speakers who willingly share with us in this workshop today, and the IEEE GRSS Indonesia Student Branch, who are the organizer for these events, and the nobles, the audiences. Let me introduce myself. My name is Edward. I am a member of the Satellite Communication Radar Laboratory of Telkom University. Here I am representing Dr. Adia Pramudita, who unfortunately unable to join us in this workshop. So the development of the nanosatellite is going rapidly. It is shown by the statistic that there are more than 1,000 nanosatellites have been launched in these last decades. One of the appealing point of nanosatellite is because it has less complex system, so almost everyone can do it, can develop it, from company down to university or school students. So this technology gives us a chance to access the space easily. Thus, the understanding of every satellite part is needed, how to build it, how to design it, and how to test it. And one of them is how to a better understanding of how to generate and manage the power for the satellite itself, for the spacecraft itself. And a big appreciation for the IEEE GRSS who conduct this workshop. So hopefully it will help the audience to understand the part of the satellite system, which I believe it can gain the motivation of everyone here to be involved in developing the spacecraft. And someday we'll try to access the space for our sake, for our nation's sake. And also a big thanks for IEEE GRSS Indonesian Student Branch who has organized this event. And last but not least, for all the audience here, please enjoy this workshop. Hopefully it will motivate you to join us in spacecraft development, whatever your background. And that's all from me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Edward, for delivering the speech. And the next agenda will be the photo session. Therefore, we ask for the willingness of all workshop participants who are present to turn on your camera. And maybe the operator may help this session. Right, in country, please give your best smile for page number 1. 1, 2, 3.
Okay, everyone, for the photo session, please turn on your camera and put your best smile. Okay, is that all? Okay, I'm gonna take the picture and at 3, 1, 2, 3, smile. One, two, three, smile. Okay, that's all for the photo session. Back to you, Lutfi.
Thank you to the operator. And thank you to all participants for participating in this photo shoot. Now, I will introduce you to the moderator who will guide the first and the second session, Mr. Muhammad Purwa Manggala. Maybe operator can help to share the CV. Right, Mr. Muhammad Purwa Manggala is work at Telkom Indonesia as Digital Telco Regulatory Management. He graduated from Telkom University and at 2011 majoring telecommunication engineering. He graduated also from his magister program from TELU in 2019, and he was a research student at Kumamoto University, Japan 2020. His academic experience, the reason is he was the nominee phase 2 of MTT-SAT Challenge by IEEE USA 2020. And also he got the student award, the SICK student award from Spacemic Mission Competition in Japan 2019. Okay, please welcome Mr. Purwa to the Honorable Mr. Purwa Manggala. Time is yours.
Thank you for the time from Mr. Lutfi. Good morning, Pak Arifin, Pak Heru, Mas Edward, and all participants here. Glad to know you. That we can gather here in good situations and in healthy conditions. So this is a chance for me to help the speaker from the BRIN or Badan Riset Inovasi Nasional that want to deliver the idea of what is the power itself, especially for nanosatellite. So we can jump to the first speaker. Let me introduce the first speaker. Maybe the operator can help to share. Okay, so this is the first speaker for today. Let me introduce Ms. Desti Suryanti. She was graduate from University of Indonesia from MIPA Ekstensi Fisika Instrumentasi that has graduated in 2010, and the master degree in the University of Indonesia from Electrical Engineering, especially in Industry Control, that has graduated in 2014. So the latest journal that she was applied and accepted is in 2021 is preliminary power budget analysis for equatorial low Earth orbit or LEO communication satellites. So we can show that Miss Desti, the floor is yours.
Okay, thank you, Mr. Purwa. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam wabarakatuh.
Can I say good morning, everyone? My name is Desti Suryanti, and I am junior researcher at Satellite Technology Center BRIN. And today I'd like to talk to you about the photovoltaic conversion and power budget calculation and implementation the power system and the nanosatellite. And also hopefully this will act as a springboard for discussion. Okay, let's start. Can I share the presentation?
Yes, please.
Is it already displayed on?
Yes. It's
Okay,
clean and
okay,
clear.
thank you. Okay, today I like to talk to you about the photovoltaic conversion and power budget calculation and implementation the power system on the nanosatellite, and also hopefully this will act as a springboard for discussion.
Sorry, Ms. Desti,
yes?
it hasn't full screen yet. So can you help us to share the full screen?
Okay. Let me check. Is it already display on?
Yes, but it's not full screen yet.
Not full screen yet. Okay. Already full screen?
Sorry, it's not yet.
Not yet. How about this?
Yes. Okay. You may go on.
Okay, thank you. Okay, I will start. Today, I'd like to talk to you about the photovoltaic conversion and power budget calculation and implementation the power system on the Nano-Satellite. Okay, I plan to speak for about the 60 minutes, and my talk will be divided into 6 sections. The first is photovoltaic conversion. And the second, we will learn about the satellite system. And the third, we will learn about power system element. And the fourth, we will learn about the power system requirement. Fifth, we will learn about power budget calculation. And finally, I will explain about the solar array sizing. And I'd sure be glad to answer any question at the end of my presentation. So please hold your question if you have any. Okay, next we go through the first topic, is the photovoltaic conversion. What is the photovoltaic cell? Photovoltaic cell used to convert sunlight into electricity for Earth orbiting satellite. Solar cell produce electricity from the light or sun. This effect is called photovoltaic. Why PV cell is important for the spacecraft? Because all spacecraft require electrical power generated by PV cell throughout the mission life without any interruption. Next, we will learn about the photovoltaic using silicon, which material widely used. Based on the following picture, silicon is most used material for solar cell, photovoltaic cell, or photovoltaic cell production. And the record lab cell efficiency is 26.7% for monocrystalline and 24.4% for multicrystalline. The highest lab efficiency in thin film technology is 23.4 for copper, indium, gallium cyanide, and 21.0% for cadmium telluride, solar cell. Record lab cell efficiency for perovskite is 25.5%. In the following picture, in the laboratory, best performing modules are based on the monocrystalline silicon with 24.4% efficiency. Record efficiency demonstrates the potential for further efficiency increases at the production level. And then in the laboratory, high concentration multi-junction solar cell achieve an efficiency 4.1% today. With concentrator technology, module efficiencies of up to 35.9% have been reached. Next, when we analyze the atomic structure of silicon, these atoms are bound together and have no freedom of movement. Pure silicon form is tetravalent, so a tetravalent structure is formed. Next, in the following picture, N-type silicon is created when pentavalent phosphorus is inserted in silicon doped. Besides phosphorus, you can also add nitrogen or arsenic to silicon. From here, additional electron can be obtained. Okay, next, when silicon is doped with trivalent boron, type P silicon is produced. Besides boron, you can also add aluminum or gallium or indium to silicon. This additional element will increase the number of holes. Next, we go to the next slide. In the picture, two types of N and P junction, N and P semiconductor, when combined, PN diode, other call it a metallurgical junction. This is the junction. Okay. Next, if these two type of dot material join together, some electron from the N, the N side will migrate to the P side and fill the available holes there. And then the type N silicon has lost electron near the junction zone, so this section develop positive potential. The P-type silicon has gained electron near the junction zone, so this section develop negative potential. An electric field will inevitably form between this potential. Next, due to the difference between positive and negative potential, an internal electric field naturally arises from the positive side to the negative side. Okay. And then this is the context for photovoltaic. And when the light impact the structure, then hits the P-N junction, something very interesting happens. The light hits the N side of the PV cell, then penetrates and reaches the depletion region. The energy of this photon is sufficient to produce electron hole pairs in the depletion region. Next, the electric field in the junction zone will push the electron from the junction to the edge of N-type silicon, and will push the hole from the junction to the edge of P-type silicon. Next, if a path is provided to electrons to allow them to recombine with holes, electricity will be generated. And then as soon as we connect any charge between this edge, electron will start through the charge. The electron will recombine with the holes in P-type silicon. In this way, current will pass through the load and the solar cell continuously provides direct current. Okay. Next, we go to the next slide. Based on the following picture, solar arrays content of the solar module content of the solar cell, and series cell build up the voltage, we can say string, and string in parallel build current, we can say array. Okay, next we will discuss a little about the satellite system. Most of the satellite system has platform subsystem and payload subsystem. On the picture, subsystem platform includes mechanical, thermal, propulsion, AODCS, sensor, communication system, power system, etc. For the payload subsystem, includes transponder, camera, lens, radar, scientific instrument, etc. Focus on the both power system. Why the power system have an important role in satellite system? Because power system provides power for every system, including itself during the whole mission. Okay, next. This one, we will discuss about the system element. On the following picture, the power system element divided into three parts. There are power generator, energy storage, and power electronics. Power generator work for generate power from external energy, most widely used from its photovoltaic conversion by using solar cell. And then for the energy storage, this refers to the accumulation of energy and its substitution into electrical form. Batteries are used for this purpose. And the last, this is a power electronic. Power electronic is charge of the conditioning, power distribution, protection, and also power monitoring. Okay, next, we will discuss about the power system requirement. Why we need to know the power requirement for satellite? Because the satellite requirement specification generally do not specify the power, specify the power system requirement. It merely includes a general statement such as the power system should generate, condition, distribution, and store electrical power to meet the requirement of the spacecraft payload and bus system during all phases of the mission. And then to meet such a broad statement of work, almost all requirements of the power system are self-derived based on the design analysis and approach taken by the satellite manufacturer. Okay. In addition, power requirements are needed to determine the size of solar panel, batteries, and EPS, or electronic power system. Then we go to the power system requirement. First, main design requirement of the power system are orbit. Which orbit to choose for your satellite or spacecraft? Is it LEO, MEO, or GEO? And then we check the sunlight and eclipse duration and then the inclination. Next, the second is mission life. How long years in orbit, the satellite years in orbit? Is it under 1 year, 2 years, 5 years, 7 years, 10 years, or 15 years? And the third, power requirement. Power requirement of the satellite system based on the operating profile of the payload. The fourth, mode of operation. Operation mode may affect battery cycle and array illumination. Okay, next we will discuss about the power budget calculation. Power budget is power utilization and consumption calculation associated with a system. It can be seen as net power balance of the system while in operation. The power generated and consumed can vary according to mode of operation. In case of a satellite, typical solar panel generate power and battery store it for use. While designing the satellite, we have to calculate how much power needs to be generated so as to cater the needs of all the electronics on board. The calculation of how much power needs to be generated will be responsible for solar panel parameter. And storage capacity of battery is also dictated by the power needs in the eclipse region of the orbit, wherein solar panels do not generate power. Okay, next, the power budget can be calculated only when entire design of all the electrical components is known. But tentative budget calculation start at the beginning. The parameter for the solar panel battery, the parameter of the solar panel, battery, and various load get fixed iteratively, and eventually the power budgets get refined. Power budget can be calculated by listing all the major components which consume some significant power. We will be calculated the power consumption of the, for the example, we can say satellite X by taking one subsystem of the satellite X and calculate the power consumed by it, and do the same for other subsystem and add them up. The ballpark values can be obtained by studying the literature of previous satellite mission, from studying particular class of component, etc. System engineer plays an important role in making and maintaining the power budget of the system. On the following table, for the example, we have 3 devices. There are GPS, magnetotorque, magnetometer, and 3 devices have 12 volt for the GPS, 28 volt for the magnetotorque, and 3.3 volt for the magnetometer. And operation current is 133.33 milliamp for the GPS, 114.29 milliamp for the magnetotorque, and 10.61 milliamp for magnetometer. To find out the amount of power from each device, that is by multiplying the voltage and the current. In the manner shown above, the power consumption should be calculated for all the major components and added to get the overall power. Next, the last section, we will discuss about the solar array sizing. The nanosatellites in general are satellites that have an low Earth orbit, with a solar array that can produce maximum electrical energy during daylight condition, and this electrical energy is used by satellites during eclipse condition. To design solar panels on nanosatellite has challenged due to dimensional limitation. However, the satellite must be able to complete its mission of the satellite operation. Okay, next we go to the typical design requirement. On the following table, first table, we have typical design requirement, which are, we have the bus voltage 28 volt, and the total voltage at solar array is 38 volt, and the power generation required for satellite is 160 watt, and required current at bus is 1.7 amp. And now the second table is cell parameter, which we use. The short circuit current, or ISC, is 456.5 milliamp, and the open circuit voltage, or VOC, is 2,690 millivolt, and current at maximum power is 441.5 milliamp, and the voltage at the maximum power is 2,409 millivolt. For power at maximum power is 1,064 watt. Next, to find out the number of cell arranged in series is by divide the total voltage on the solar array with the voltage at the maximum power, and for this result is 16. The number of cell in series is 16, and to find out the number of cell arranged in parallel is by divide required current at bus with the current at maximum power, and the result is 4. The result for the number of cell in series and number of cell in parallel is 16/4. It means one panel has 4 string, and each string have 16 solar cells. Then the power generated by one solar panel is 64.6 watt, assuming the solar panels are mounted on the satellite body and always point toward the sun. Okay. Next, this concludes the focus of today's discussion. To end, I'd like to highlight, in addition, at the end of life, the array must generate required power equal to the sum of all loads, the power losses, and the battery charge power with some margin. To calculating the solar panel requirement, it is necessary to add a margin in the power budget calculation. Margin plus initial power capacity minus degradation must be greater than maximum power requirement at worst condition. Okay, I think this is the last page. Thank you very much.
Thank you, Bu Desti, for the marvelous presentations. That it reminds me actually, Bu Desti, about my latest project when I was in Japan. That I made the metal sphere for the solar panel that enhance the absorptions and also the scattering of the solar panel itself to enhance the capability of silicon. So first thing first, let me highlight some of the presentation that Bu Desti shared. The first is about the material structure of silicon that has a certain characteristic that applicable in space, and the second one is the satellite system, especially for the power generator that has the energy storage and power electrical, that it has to be into account with the requirement of pilots and also the bus or the platform that BRIN said. And we have to acknowledge that there is an eclipse or the sun's durations and also some inclinations based on the orbit that we have to calculate and it affects the number of the solar cell or the dimensions of the solar cells. So in here, there is a participants that asked about what the safety margin for safety maximum for operations. Maybe Bu Desti can share the idea of it.
Okay, I already read the book of the satellite power system. For the margin about the power is around 3 until 7%.
Okay, 3 until 7%
Yes.
for the worst case.
Yes. Yeah.
Okay.
Maybe we can read on the book of the satellite power system.
Okay, 300. That is applicable for the every orbit and also every missions, or it's only there is a guidance that okay, it's applicable for 10 is if this is for the nanosatellite or something like that.
Yeah, I think it is applicable for lay satellite with LEO orbit.
Okay, satellite LEO orbit.
Yes.
Okay, because if I'm not mistaken, maybe it will be addressed by Mas Andri at the end of the third sessions.
Yeah.
Because me and Mas Andri actually was a partner for 2 years ago that we have been together for operational satellite for TELKOMSAT. We have to spend at least 20% of margins there. Yeah, if it's going to sell it lasts 20 or 30 margins, we have to going to the safe mode. Like it's not really a safe mode, but it have to make a simple mode operations or something like that. Maybe it will be addressed by the third sessions.
Yep.
Okay, and the second questions from Mas Sabri Khairul Akmal, and he said that what durations on ADCS power calculation come from? So yeah, so how do we know the durations of ADCS calculations?
It depends. Okay, the duration of the AODCS it's depend the operation the mission operation, which for the maximum duration it depends on the orbit and the altitude. For the example is our satellite in altitude 660 kilometers. We have a maximum duration 1.63 hours. But if we choose the maximum duration, we worry about the power storage. I think like that.
Okay, it's about the power storage. So maybe I would like to confirm you. Is it the main the most consumed module in the satellites AOCS, or there is another module that consume more power than ADCS?
Consume more power is if we satellite transmit the data from the satellite to the ground station. It is most we need the more power than AODCS.
Okay.
For the payload system, in our experience, we need around 100 until 120, 1,000 and more watt to transmit the data.
Okay. And those number of the power consumptions is expected if we transmitting the raw data or the hex data or the image data from the satellites.
For our previous satellite, I think we send the raw data.
Okay.
But it depends the engineer, or it depends the researchers.
Okay. And for the calculation itself, is there any differentiations of the number or how big or how huge the difference of the power of budgets consumptions if we have a different payload or different orbit?
Yes, of course, because the payload have some different power consumption, like APRS, AIS, and camera. If the satellite bring the camera on the satellite, we need the more power than the satellite with the AIS.
Okay, I see. Okay, we can jump to the third questions. There is a question from Mas Edward. He said that a lot of toys using solar cell nowadays, and it can be easily found on the market. Can it be used for satellite applications, like the solar cell for the house or for the green fields? Is it applicable for satellite?
For the solar cell for the satellite, it's I think it's different with the market for the. I think solar cell for the satellite is different, and we can contact the provider, contact the vendor, because we have the different criteria for the satellite and for the for the in ground. Yeah, I think in ground. Yeah, it's different because in the space in the space we have to focus about the voting, about the temperature, about the environment. It's different.
Okay, so at least we have to accommodate the solar flare or the most maximum and minimum temperature, and also the percentage of absorbing, maybe. Okay, we got it for the third questions, and actually there are a lot of questions, and maybe we can jump to the we go to the fourth questions. Desti?
Yeah.
Okay, so let me read the fourth questions.
Yeah.
So what parameters that we need to monitor to make sure the health of the solar array while the spacecraft is in the orbit operation? So this is from Mas Fasni. So.
Okay, about the health of the solar panel. In the data sheet of the solar cell, we can check the degradation of the solar panel, solar cell. Yeah, if the output generate, if the solar output generator of the solar panel decrease. So I think the health of the solar cell is not 100% like new.
Okay, so one of the perspective that we have to maintain
Yes.
is the temperature of the solar panel. Or
maintain of the temperature of solar panel, because the solar panel have the temperature sensor, so we can monitor in the ground station when the operator operate the satellite and get the telemetry. We can see the value of the output of the solar cell.
Okay. That's clear questions. Maybe Ms. Fasni can find the temperature for the solar panel. Maybe we going to Pak Heru questions first.
Yeah.
So Pak Heru asked about what are the causes of the decrease in the efficiency of photovoltaic conversions efficiency. What is done in the manufacture of solar cell is so that the decrease in efficiency is not too deep. What also needs to be done in the use of solar cell for satellites, so the efficiency is almost maintained properly. For the mentioned degradation of 3 to 7% from the BOL beginning of life to end of life of the satellite will occur in how many years?
On the data satellite show for the degradation for the I think 5 years. 5 years.
For 5 years. So
yeah.
What about the cause, or what is the main cause of the decreasing of the efficiency in photovoltaic conversions?
I think I can answer because I don't know about the degradation, decreasing the efficiency. Maybe it caused the environment, extreme environment, or maybe
yeah, okay, because we cannot see clearly what is the environment in the space, so sometimes there is unexpected failure, like maybe even like a failure, then unpredictable failure or something like that maybe can cause the decrease in efficiency. Another sides of the aging sides of it. Okay, so for 5 years, maintaining degradations from the beginning of life to the end of life, so it's quite enough for LEO satellites, for operating the satellite itself, to running the missions. Okay, thank you, Pak Heru, for the questions. We can back to the next questions from Mbak Tiwi Rahma Mulia. So she said that, are there any internal influencer during the orbit that can affect the power system, and how to solve the problem?
Sorry, Mr. Purwa, can you repeat this question?
Okay, so if I'm not mistaken, to read the questions is, are there any external influencer during the orbits that affect the power system? Like, is there any environments that affect the power system besides the failure inside the satellite itself?
I think it is radiation, radiation, and when we connect the solar cell, I think it is can decrease the value of the solar cell. And another is
Maybe asteroid? No.
Asteroid, I don't know asteroid, but I think its radiation is the first,
Okay.
and the extreme temperature, and I don't know.
Okay, so at least there are two. The first is about the radiations and also the temperature. So so that's why we have to see at least the temperature sensor in the housekeeping that come with the telemetry to the ground. Okay, I got it. And this is the next question, or maybe this is the last questions. Hello, Ma'am Desti. I'm Ahmad Farizal Ramadan, who enthusiast for orbital satellites. Wow, nice to know you, Mas Ahmad. And he said that is it different use a solar array for different orbit like Leo, MEO, or GEO? And could you tell us how long in general durations minimum of maximum of solar array, and how solar array know is it already full by the sunlight? Thank you.
For the Leo satellite, for the example is our satellite with the altitude 660 kilometer to the for the Leo satellite, the satellite will what is it?
Yeah. For Leo satellite, it will be orbiting faster than the GEO satellite.
Yes, of course. Yes, I mean, will faster with the MEO or GEO satellite, because the velocity of the Leo satellite is fast than the MEO satellite.
Yeah.
And for the one day, the Leo satellite will, I think, around 14 or 12. What is it?
Repetition for a day?
Repetition, yes, the repetition will 12 or 14, I think.
Okay. Okay, so the difference orbits that from Leo that maybe, if I'm not mistaken, you mentioned from 400 until 800 kilometers is Leo is going to orbiting or fully repeating the Earth's about four times, or how many times in a day?
For the Leo satellite, 12, I think 12.
Okay.
Yeah.
Okay, for Leo satellite will be going 12 in a day. Like rotating the Earth. And for GEO is
same like the Earth rotation for the GEO.
Earth rotation. So so is there any different use of solar array, or is it same? It's I mean, like examine the number of solar cells itself.
Yeah, for the Leo satellite, we major dimension is small and micro. So it the dimension is effect for the design of the solar cell.
Okay. Okay, so there is a different size of satellites in Leo. So the number of solar cell that the phase the sun, it will be different number with GEO, and also maybe because of maybe we can see the eclipse
Eclipse duration and sunlight duration, because the on the Leo satellite we more meet the eclipse duration.
Okay, because when a Leo satellite rotating the Earth, maybe there is the huge probability that satellite cannot face the sun, rather than the GEO satellite that the eclipse is only in certain period.
Yeah.
Okay, and this is the last question from Pak Arifin Nugroho. Thank you, Pak Arifin Nugroho, for the questions. He said that in the view of obtaining higher efficiency, do you require a control attitude allowing the suitable space orientations of solar panel?
Yeah, sorry, can you repeat the question, please?
Okay. In the view of obtaining the higher efficiency, do you require the control attitude allowing the suitable space orientation of solar panel, like in the certain of the satellite, especially in the low satellites, they are mounting in the body of a satellite. So Pak Arifin want to discuss about, is it required to control attitude allowing the suitable space, so control satellite for the solar panel?
Yes, we discussed with the AODCS engineer, because our satellite check the available space maybe for the payload antenna gitu, and we only have the small space and we need the more power, so the solar panel will install on the body mounted or deployable solar panel. If we combine the solar panel installed in the body mounted or deployable, so we have to discuss with the AODCS engineer to what is that? To check how the operation the satellite, is it the momentum bias or the sun pointing or what else like that.
Okay, so let me continue the question. So if it's required the control attitude, so is it affected the power consumed by the ADCS itself? Maybe like, because in the certain we just keeping the inertia momentum and something like that. So but
yes.
if we control the space for the solar panel orientations,
yes, is it effective? Because for the AODCS, maybe if we want a solar panel pointing the sun, we have to maneuver the satellite, so we have to turn on the reaction wheel, maybe 3 reaction wheel or 1 reaction wheel. It affect for the power consumption.
Okay, thank you, Bu Desti, and thank you for every single person that share the idea or the constructive question for me and Bu Desti. Maybe the last question, Bu Desti. So may we know the latest project that you do right now in the BRIN for a satellite? Yeah, maybe we haven't heard yet.
Yeah, currently we are working on the 8F satellite, and I'm in charge on the satellite power system, and my leader is Mrs. Eri, will be presented after this section.
Okay.
And now for this year, we waiting for we want to procure of the solar cell, and we will try to assembly by ourselves.
Okay. Maybe Mas Edward has a solar panel in the Nanosatellite lab in Telkom University. Yeah, maybe we can from the student, maybe we can send some students to learn from you, because if I'm not mistaken, in Telkom University Nanosatellite laboratory we have a solar panel, but nobody hasn't touched it yet. Yeah, I can say touch it yet because it's still in the safe box and waiting for the person who use it. Okay. Thank you, Bu Desti, for the marvelous question and answer sections, and also the inspiring presentation from us, especially for me. Okay, thank you, Bu Desti.
Thank you, Mr. Purwa.
Yeah, and let me help everybody here to introduce the second presenter today, and let me give the floor for Ibu Ray Fitrianingsih. Okay, can moderator show? Can the operator show the CV of Bu Ray? Okay, so this is the second speaker, Bu Ray Fitrianingsih. So she was the researcher in space field with more than 10 years experience in satellite program, and she has a strong interest in astrodynamics, satellite program, satellite system design, mission analysis, and space environment. So, it's a complete system environment. Okay, Bu Ray works in BRIN since 2003 for the researcher, especially leads space segment group for the Indonesian low Earth equator satellites constellations. She was graduate from the ITB, right? Yeah, ITB, the bachelor degree in aeronautics and astronautics, and she continued in master science in space study in International Space University in France, and the latest education is Ph.D. in electronics engineering in University of Surrey. The latest project of Bu Ray is Indonesia's low Earth equatorial satellites constellation. So let me give the time for Bu Ray. The time is yours to present the idea. Thank you.
Thank you, Mr. Moderator, Mr. Purwa. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Distinguished Honorable Mr. Arifin Nugroho, the organizer of this workshop. Thank you for inviting me to give a talk today. It is exciting to see that there are many space enthusiasts gathering today instead of having a day out during this weekend. So let me just a little bit clarification about my education. I do graduate from I have a degree from electrical engineering from Surrey University. However, my research actually has nothing to do with electronics. So I have very limited knowledge in electronic engineering actually, because my project during my doctoral degree is related to trajectory optimization. So actually today we have also Mr. Karim from BRIN, who is an expert in the EPS, but today the organizer inviting me to give the talk. So I will share a little bit of my knowledge today about what I understand about the satellite battery and also the EPS based on from my experience working on LAPAN project. Okay, let me share my presentation.
Yes, please.
Okay, is it visible right now?
Yes.
Okay, so today's talk, I will focus on two things which is required by the organizer. So first, I will talk about satellite battery technology and stabilized DC power system, and on the second part, I will I will share my knowledge about the EPS design and implementation. So we'll start with the first part, which is satellite battery. So we all know that in order for a satellite to operate in space, it needs electrical power so that satellite bus and payload can do what is required from the mission. The main power source in the Earth orbiting satellite is solar power. But however, there is an occasion where the satellite in orbit enter an eclipse condition in which the satellite solar panel can not get any illumination from sunlight. So in that case, the satellite needs to rely on the secondary power supplier or power source, which is a battery. So what is the difference between the battery that you use in on ground and the battery that you use on satellite in orbit? So the main difference is actually the environment that the battery will experience. In the space environment, the battery will have to deal with the radiation in the form of total ionizing dose and displacement damage dose. And this both of this event may cause component degradation, and also single event effect and deep dielectric charging, which also might damage the battery electrical component. And the second one, in the space environment, the satellite will have to deal with the vacuum condition, which cause and the phenomena that called outgassing, which is the pressure outburst from a component and cause a failure. And the third one, and the temperature that will be experienced by the component, the battery, is very much different from temperature that experienced by the battery on the ground. In orbit, it's depend on the altitude and the inclination that the satellite fly, but the temperature, the surface temperature of the satellite is varying very significantly. So it may reach minus sub-zero degree until more than 50 degree. So that's why the battery has to be able to withstand the extreme temperature in space, and also the vibration during the launch of the satellite. It is also something that the battery, especially mechanical part, has to deal with. Okay, so now I'm going to talk about the primary, the type of battery that we use in small satellite. In the small satellite, there's two type of battery that type of battery that can be used. The first is the primary battery or non-rechargeable battery, and the second one is the secondary battery. The characteristic of the primary battery is it's a very short use, usually during launch or shortly after launch, or for extended period of very small power consumption. Usually, it has a very high volumetric energy expressed in watt per meter cubic, and gravimetric energy or watt per kilogram. But the capacity loss is very, very fast. So it can reach 60% of the capacity loss per year compared to the initial capacity. So that's why it is not suitable for to be used as the primary source for in-orbit operation. So the many example of this primary battery, including EGZN, LiSO2, LiPCX, and LiCFX. And the other characteristic of this primary battery is the wider operating temperature range, around minus 40 to 70 degrees Celsius. And the most common one to be used in small sat is secondary battery. I think many small satellite mission prefer to use secondary battery, and in this type it is dominated by a lithium-based battery. As we can see on the figure on the right side, that is we have a comparison between several types of battery cell. For example, lithium-ion, nickel cadmium, and then lithium chloride, and lithium polymer. So until now, the lithium-ion is still the most favorable to be used for small satellite mission by 66%, and also because it's the same. I mean, basically lithium-ion and lithium polymer is almost the same. So the lithium-based battery is dominating the use in a small satellite. And why this lithium battery is favorable by many satellite designers is because the energy and power density is significantly higher, about 2 to 3 times to nickel based cells. And also, for example, COTS battery, which is a battery available in the market, which is not dedicated for space environment, it's usually weighing on around 50 grams per cell, and the average voltage is 3.6 volt, and the density is can range from 252 watt-hour per kilogram up to 762 and 762 watt-hour per liter. So this is a little bit about the lithium-ion cell. So in the market currently, there are space-qualified lithium-ion cell, which is widely used by a small satellite developer. So one of the brand that is well known and proven in many space missions is the battery cell from SAF. But however, some space company that offer a battery pack or battery module, usually they also offer battery pack that based on COTS cell, which is typically used 18,650 cell type, because the cost is of course lower because it's COTS. So, but now this COTS-based battery has been widely available in the market, and it's already proven in space in many satellite missions. So I recognize two of the company that they have two COTS battery module in their line, is ABSL and also Eagle Picture from Eagle Picture Technology from the United States. And then this both are reputable company, and their battery based on COTS cells also is already flight proven. So this is about COTS based battery. From my literature review, what I understand is that there are three major brands that is already used in space for space mission. So the quad cell, they have the same type, 18650 cell, and Sony VTC. This is used by ABSL and LG, and also this on NCR is used by Eagle Picture. So the difference between both battery is the maximum discharge rate versus the nameplate capacity, which is the capacity of the battery cell. So as we can see here, the Sony battery has the highest discharge rates, which is around 30 amperes. But however, at this maximum discharge rate, the nameplate capacity is the lowest compared to the LG and Panasonic brand. So the Panasonic has a higher capacity, but the discharge rate is not as high as Sony or LG. So it will be depend on our design to select which one between this option. If you want to use the quad-based battery, which one is suitable for our need. So of course the trend in small satellite inclined toward the quad component, because it significantly reduced costs. It also applicable in the battery, and to deal with the space environment, although the COTS component, the COTS cell, is not dedicated or tailored for a space environment, but we can apply some special treatment on the casing of the battery itself to be able to withstand all the hard space environment. The characteristic of the lithium-ion cell. When it is exposed to the sub-zero temperature, the capacity during discharge and rapid reduce very significantly, and the cell also degrade rapidly. At low temperature, the lithium-ion battery internal resistance is rapidly increased, causing the major voltage drop that limit the discharge by reaching the battery minimum voltage very quickly. So as we can see in the graph on the right side, this is a graph for several conditions about the impedance versus the temperature. As we can see, if the temperature, if the battery exposed to the very extreme sub-zero temperature, like -40, the impedance going very high, and it is of course will significantly reduce the capacity. And in particular for polymer battery, as we can see here, it at -10 degrees Celsius, when the temperature reach -10 degrees Celsius, the impedance is already reached 1 ohms. So I think this is the limiting factor why it is important to keep or to maintain the temperature of the lithium polymer battery, and actually every battery has to be maintained on a certain range, certain operating range, so that the capacity will not decrease significantly. So okay, now about the lithium polymer cell. I realized that some of leading vendor or leading company in Nano-Satellite provider, component provider, offer or prefer using lithium polymer cell in their batteries. And one of the reason is because maybe the low energy density compared to the lithium-ion battery is lower, but the shape is it's not cylindrical like lithium-ion. So with this, because the shape is wide and also thin, it can be stacked and so that it can overcome the issue with the size that usually faced by nanosatellite. Because as we know that nanosatellite is a very small system, so it has to be careful when selecting the battery or all their components so that it can fit in their system. Generally it's lightweight. I noticed that some of the company like Indorosat and Clyde Space, they offer a battery pack or battery module based on a lithium-ion cell. This is one of the lithium-ion based small satellite battery that I mentioned. It's Optimus 80. Sorry, this typo here is Optimus 8, offered by AAC Clyde Space. As you can see here, the mass is very low, is less than half kilogram, and the length, the width is also small. The height, it can offer a capacity up to 30 watt-hour, and then but it works on the voltage of 8.26 voltage, and it's based on lithium polymer, and the discharge currents it's typical, it's 1.95. So this system, this battery system is optimized for LEO orbit with maximum altitude of 850 kilometer, which is I think most of nanosat will are flown below this altitude, and they have an excellent track record in orbit. And this battery system is also have an autonomous integrated heater system to enhance operation at low temperature, which is I already explained why it is important to maintain the temperature so that the capacity do not drop significantly. So this battery, because it's lithium polymer, is also equipped with a protection system at cell level and battery and system level, which respond to external fault condition in order to protect battery so that it won't completely fail or prevent from irrecoverable damage. This is an example of a lithium-ion quartz-based battery. What I shown here in my screen is a Eagle Picture quartz battery based on Panasonic and LG cell, lithium-ion cell. So the battery mass is quite big because as you can see, this is a big pack actually, but it can provide the specific energy reach 75 to 100 watt-hour kilogram. It's a big pack, and it is used if we demand quite high capacity for our system. Also, we can see here, this is battery pack voltage, 14 to 48 volts, which is from this we can also see that it is not, maybe it's not very suitable for nanosatellite use, but it's more for small satellite use, because I know that typically the nano-satellite voltage use 3.3 for their electronics and around 5 or 6 for their payload system. So, but the Eagle picture, I think they have an option for a smaller pack than this. Okay, so to summarize, the difference between the lithium-ion and lithium-polymer battery cells. First, that the electrolyte itself, they are basically the same lithium-based battery, but the electrolyte is different. And in the case of lithium-ion, they use liquid electrolytes, and in lithium-polymer, they use porous chemical compound or gel-like electrolyte. In the past, they use solid electrolyte, but it's no longer. I mean, the product is discontinued. And the shape itself, usually the lithium-ion take cylindrical shape, while lithium polymer usually in the shape of a pouch. And with lithium-ion and lithium polymer, we don't have to deal with the memory effect, which can cause battery to hold less charge over time. Maybe I think all the participants here familiar with the memory effect, in which let's see, if we charge the battery, if we don't fully charge the battery and we start using it, and then on the next the capacity, the full capacity will be decreased from the initial capacity. The lithium ion is cheaper to produce compared to the lithium polymer, but the efficiency of a lithium ion battery is decreased with time, even when not in use. So this is important because I have read some chart of the capacity fate. For example, if we want to flow our battery, like let's say next year. So in 1 year, typically the capacity will already drop to 90% compared to the initial capacity. And the lithium, even if it's not used, even if it's, you just put it in the storage, and also this capacity is will decrease significantly during the lifetime in orbit, and the drop is very the reduction is very significant. So it is a factor that you need to consider when you do the sizing of your batteries. And because the lithium ion also prone to overheating, so it needs a protection. We need to implement a protection circuit battery in the battery management unit. Lithium ion is famous for the characteristic of unstable in high temperature. We read some cases in the internet that the battery with this overheat just explode, and this is something that we need to consider. And the performance of the lithium-ion battery reduce when the temperature is too low or too high. So we have to maintain, we have to make sure that we maintain the temperature of the battery within the operating temperature range that is specified by the battery manufacturer. For the lithium polymer, the production cost is comparably higher than lithium ion. It's around 10 to 30%. So this is also something to taken into consideration when we need to when we want to select the battery that we are going to use. And the shortened span or charging cycle, typically 200 until 300 cycle. And compared to lithium-ion, the lithium-ion can reach 500 cycle, but I think right now Tesla, I think they develop a lithium polymer battery, and which is can significantly increase the number of cycle for their lithium polymer battery. So maybe in the future this figure will change, and lithium ion battery may be favorable, more favorable to be chosen for space mission. So when we select the battery, the main consideration is that we need to consider the cell type, what kind of cell we want to use. Is it lithium-ion, lithium polymer, or nickel-based battery? But in order to choose the cell type, we also need to consider how the mass of and the size of the battery itself. Excuse me. Maybe. Sorry. And then the second one is the DOD, or the depth of discharge of the battery. I will talk a little bit more about the DOD on the next slide, and capacity of the battery itself. I think we are all familiar with the battery capacity. It's expressed in ampere hour or watt hour. This capacity is one of the most driven factor when we do the battery sizing, because we need to make sure that the battery that we size will be able to operate under the worst case load condition. And then the other consideration is the battery cycle, or the life of the battery itself. Mr. Desti already explained that in LEO orbit with altitude around 600, the satellite will pass the Earth 14 times, and in every orbit, the battery will experience. The satellite will experience eclipse and sunlight. So, so in one day, the satellite will have 14 cycle. And if we need to times that into the duration of the lifetime of the satellite that we expected, and how many cycle that going to be experienced by our battery, and that's going to be one of our consideration in selecting the battery. And then of course the voltage, as I show an example in a previous slide, we need to also consider the voltage of the battery, because not all product in the market is suitable for our requirements. So we need to be careful. We want to have a battery that is matched with our voltage requirement, and also discharge current, also one of the main consideration in battery selection. So in the table on the right side, we can see comparison between LEO, MEO, and GEO requirement. In LEO, in GEO, of course, we don't have so many cycle per year. It's only 180, and the lifetime. But in GEO, the lifetime is we are expecting that the battery can last up to 14 years, because GEO satellite project is a very expensive, and you don't want to fly a satellite that only last up to 2 or 3 years. So you want to have to fly the satellite and take advantage of the mission as much as long as possible. And the charge current rate in LEO is typically 0.33, and the DOD is between 10 to 40%, and discharge current linked to cycle is 0.5 up to 0.7. And the temperature range is 0 up to 40. But all this data here is average. It can be vary depend on the orbit that we select. So just to clarify a little bit about the depth of discharge in lithium battery, why is it important when we do the battery sizing? Because it's indicate the percentage of the battery that can be discharged relative to the overall capacity of the battery. So when we relate it to the state of charge, it is complement to the state of charge, indicate DOD is equal to 100%, which is full capacity minus the state of charge. And the lithium based battery can be theoretically, the lithium based battery can be discharged up to 80 to 100% DOD, but this is theoretically, but it's not recommended. No manufacturer will recommend to have this much DOD, because it if we completely drain the battery, it will shorten the battery life cycle. So as we can see here, the relation between expected average cycle and the depth of discharge. We see here if we have 100% DOTL, we can expect the life cycle to be around 600 to 700. And if we only discharge the battery just a small amount compared to its initial capacity, the battery will last longer. So the expected cycle will increase. I think that is the last slide, the last part of my presentation about the battery. And now I will want to talk about the second part, which is the EPS, electrical power subsystem. So EPS, what's EPS? EPS is the satellite subsystem responsible for providing, controlling, and distributing electrical power to all the satellite subsystem. And it's very critical since the failure in EPS may lead to total loss to the space mission. One thing that I realized when I have to find a manufacturer or a component provider for the EPS, that some nanosatellite companies, they use the term EPS and PCDU interchangeably. What they actually call EPS is actually what we refer as the power distribution and control unit, while the EPS itself is actually consists of 3 major elements. The first is the power source or solar cell, and then the power storage, the battery, and then the power module itself, the power monitoring, control and distribution network, or PCDU. And this in some satellite mission, to simplify the design, this PCDU is integrated inside the OPTH, but it is also a common practice to separate, to have them physically separate physically between the OPTH and PCDU. As any other subsystem, the EPS design is an iterative process. When you start the preliminary design from scratch, everything is based on assumption. You are assuming what subsystem that you are going to use. You use a typical value for the power consumption and power. The load, and you make assumption what the configuration of satellite will be, what is the satellite subsystem will consist of, and this actually it is a starting point, but it needs to be iterate as the design process goes further. So the more we progress into our design, we obtain more information, we obtain more accurate data from a component, and it has to be analyzed iteratively. And during the preliminary design phase, the satellite configuration is defined. All the subsystem that will be used, orbital parameters, we expect that the satellite will be flown in which altitude, what inclination, and what is the shape of the orbit. And then during the preliminary design, we also have to assume what is the operation scenario that our satellite will conduct during its lifetime. So what I mean by operation scenario is how, for example, the payload. Okay, if it's a geo satellite, the payload will operate in like 24/7, but that's not the case for low Earth orbit. For example, if your satellite is imagery and in it only take an image for in certain area, and other in other area it will be shut off. Of course, it will also have an impact on the power load itself. So that's why we need to be able to define, even if it's this is a preliminary concept. We need to do this, defining this operation scenario to be able to do the power system sizing. And then after we have the satellite operation scenario, we can calculate the required power and do the preliminary sizing for solar panel and the battery. And the output from the preliminary design is that we will have the power system specification. We know the solar cell type, configuration, and then the battery itself, the type, the configuration also, and also the voltage that we will use, the bus voltage that we will use, that we can use that to as an information to do the iteration on the next step. So for power system sizing principle, you need to do the balance energy between the collected energy from solar panel in worst case condition and the energy consumed by satellite bus and also payload. So that's why is it not balanced power? Instead it's balanced energy, because like I said, depending on the operation concept that you define, every single component in the satellite will have different duration of on or off condition, and when is it with this operate. So it will affect the total energy that the satellite will require. And then during eclipse, of course, as mentioned before, that the batteries shall supply the required energy, because the energy that comes from a solar panel will not be sufficient, and then the battery shall supply also the needed energy during post-launch maneuver. So a little bit about eclipse, why we need why eclipse duration is also important. To understand the eclipse duration, or to be able to calculate the eclipse duration, we need to information about the altitude, inclination, and eccentricity of our orbit. And around 600 kilometer, the satellite will experience roughly 35 minutes of eclipse and around 65 minutes of sunlight. So during the sunlight, of course, that is the time that we can use the solar power to directly power our payload and our bus, and also to charge our battery. But during the eclipse, when the satellite enter the eclipse, it will not have any sun light, and of course it will have to rely on the battery. So we need to this information to be able to do the balance energy analysis. So more about the output from preliminary design phase. As I mentioned, we expect to have the solar cell specification, the type, the area, the mass, and efficiency degradation. And of course, we will know the current, after we select the solar cell type, we will get the data about the IC, the VOC, IPM, and the VPM from the manufacturer. And after the sizing, we will expect to be able to define how many number of solar panel we need to implement on the satellite. Where is the position of the solar panel? Is it mounted on the body, or it needs to be deployed to get more, because of the satellite require more power, and also the orientation itself of the solar panel. There are two approach to do the orientation of solar panel. We can use full body rotation, just to point the satellite into the sunlight, or we can implement solar tracker, so that only the solar panel will rotate toward the sun. That's why to maximize the energy. This is actually a trade-off, because I follow the discussion between Mr. Purwa and Ms. Desti about the orientation of the solar satellite to have more energy, but we as a consequence, we also require more power to maintain or to orient the spacecraft. So of course this needs to be analyzed carefully, so that the extra power that we can get by reorienting the satellite will not is still greater than the power that is required to maintain the ADCS system to orient and stabilize the satellite to the solar source. After the preliminary phase, we also expect to be able to define how the number of cell and the configuration of the solar cell in series and parallel, and we can estimate the total power and energy available at BOL and EOL. So BOL is the beginning of life of the satellite, and EOL is the end of life of the satellite. So this total power, of course, it will be depend on the how much illumination achieved by the solar panel. So it really depends on the orbit and also the orientation of the satellite itself. And also from the preliminary design phase of the EPS, we can expect that we define the battery sizing, the type of the battery, the capacity, voltage, current, DOD, and the configuration of the series and parallel cell. So to summarize the design process, we start here. We make a calculation of the power budget. We start with the orbit parameter, defining the orbit parameter, and then we calculate sunlight and eclipse duration. We define the bus voltage, and we estimate the power, estimate or assume the power consumption depend on the scenario that we define. And after that, we do the solar panel sizing. We can select the type, number of cell, configuration, and panel placement. And also we can get the voltage and current out of the solar panel, solar cell. And then we continue after we defining the size of the solar panel. We can continue with the battery sizing, the battery type, capacity, DOD, voltage, and configuration. And every single calculation here need to be verified. So the most common method is we do a simulation, power output versus solar angle and energy balance, require power versus available power, and you can use there are a lot of software, simulation software out there, even including the free software. We can search available that we can do the simulation to verify if our EPS is already meet the performance that we expected. And after that, we can continue with the PCDU design. So about the PCDU. So this is the important part of the EPS system. So because this is the part that will control and distribute and regulate the charging from the battery charging from the solar panel, and then distribute the power to the device, to the component for the satellite bus and also for the payload. And it also has the responsibility to monitor and protect the satellite power bus. And usually it control battery charge regulator, and also EGSA panel, which usually use when the satellite is still on ground. So this is just one of the example of the PCDU. I take it from University of Oslo, one of their publication. So this system actually implemented on Cube satellite, a CubeSat, I believe. So we see here the power source from the solar panel, and it goes to the power and regulation and control, and the power goes to the storage cell, which is a battery, and then it distribute everything into the solar the device in the satellite. So what I show here is just an example of the PCDU available for CubeSat in the market. If you don't want to develop it, instead you want to be a system integrator, you can. There are plenty of nanosatellite company that develop PCDU. One is Indosat, and then Avionic and Applied Space. This selection criteria is something that I myself usually use in the beginning. In the beginning of the selection process of the PCDU. So the first is the capacity of the power management, because we have every satellite will, every mission will have a different power management requirement. For example, in our case, I believe in satellite 8A5 satellite, we have to deal with capacity up to 600 watt-hour, I think, and then we also need to check the bus voltage for primary and the secondary bus voltage. As I said, nanosatellite typically they will not use very high bus voltage, but for a higher for a bigger satellite, we sometimes use 28 volt as our bus voltage, as the primary bus voltage, and then the secondary bus voltage is depend on the device that we put on the satellite. But usually the module is ranging from 3.3 until 5 volt. And then we also need to check if this available on the market PCDU is comply to the with the electrical interface requirement, and the mass and size is also we need to check that, because sometimes it we don't have we need to keep the mass and size of the component within certain range, so that it is within the constraint that defined by the mission. And then this is either free component is actually something that we it is important, because we don't want to deal with either component is going to give a lot of difficulties. So that is some of the selection criteria that we apply when we selecting available on the market PCDU. Of course, for nanosatellite, if the concept of operation is not very complex, you can develop your own PCDU. I think that end my presentation. Hopefully, what I shared today, all the participants can benefit from my presentation. Thank you, and I return the floor to the moderator.
Okay, thank you, Bu Eri, for the compact presentations from the battery that we can see clearly the characteristic of each battery, lithium, lipo, and nickel cadmium, and so on. And the second one is about EPS system that are presented by Bu Eri. So first thing first, Bu Eri, let me ask you about what is the battery type and also the EPS module that are used in LAPAN nowadays.
LAPAN, okay, in LAPAN have a lot of satellite series from LAPAN A1 until now. Under development is LAPAN A4, which is almost launched very soon, and LAPAN A5 is still in design process. LAPAN A1 up to LAPAN A3, the battery use the space grade battery, which is the cell I believe came from SAF manufacturer, and this battery is tailored to our needs. So whatever capacity that we need, we say to the manufacturer, please developed for us this kind of battery that has this certain capacity. But something tailored, of course, it's very costly. So in 8E5, because we have a short in our funding, we need to take a different approach. So in 8E5, that's why we look more into COTS battery, and what is available in the market is that's to save some of our budget, because tailored product is expensive. That's why in 8E5 actually we only, I think our requirement itself is only around 18 ampere hour, but because in the market, which is the battery that is available, it's difficult to find something that that has certain capacity. So we have to take what is the market offer, and that's why our battery is slightly bigger. Our battery capacity is slightly bigger than what we are required.
Okay, so there is a concern of budgets, and there is availability of the battery in COTS in the market, so it's easier to find the good battery, maybe because we have some limitations. So thank you for the answer for my questions, Barry, and we can jump to the questions from the participants that Mbak Tiwi Rahmat Mulia asked about. Does the battery have an effect on change in air pressure, and what kind of battery design that does not pollute the atmosphere?
Just to clarify, is does the battery have an effect on changes in air pressure? You mean the pressure of atmospheric pressure, or is that?
Yes.
Okay. So I think it is not significant. The pressure of the battery, even if no, I don't think it's something that we need to concern about. It's not going to be significant. And what kind of battery design that does not pollute the atmosphere? Well, I don't think it's pollute the atmosphere, but the satellite itself is it can be a debris if we don't remove, including the battery. I mean, I don't think the battery will pollute the atmosphere. No, I don't think so.
Okay, maybe it can be the pollute if the battery is failure, so we can work. So how to minimize the effect of the battery failure? So as the question of Mas Edward said, that what is the method to maintain the battery temperature?
Okay, to maintain the battery temperature within certain range, we can implement passive or active thermal control, or TCM. Depends on the design of the battery. Some battery you can have the heater inside the battery. It's integrated within the battery pack, and you can also design the battery to have a heater not inside the battery, but to control the whole temperature of the satellite inside itself.
Okay, so in the passive component that using the isolations and color coding, isn't it?
Yeah. You can there are many options for thermal control. You can use active control, but of course active control will require power. And also you can use isolator or MLI to isolate the temperature inside the spacecraft.
Okay.
Yeah.
And this is the third question. How does the Nanosat EPS change the power source during sunlight to eclipse transitions, or eclipse to sunlight transitions? So there is a possibility of face the sun, or there is a sun and there is no sun. And what does the operator needs to do to make that the power transition is nominal? So maybe if it's possible that we can spare it with Leo and Geo.
Okay. How does the Nanosat EPS change the power source during sunlight and eclipse transition? So this is when the battery regulator or PCDU came into play. The PCDU will automatically detect when the voltage of the solar panel fall below a certain range that we define. So, and if it's below and it's lower than a certain value, it can no longer charge the battery, and at the time the satellite will know that it's in eclipse condition, and it's going to switch on to the battery as the main source. And the second question: what does the operator need to do to make sure that the power transition is nominal? Can you clarify this question, Mr. Purwa?
Yeah, because when we are when we are not using the certain modes, there is a possibility of the batteries drop automatically because we cannot control the number of the power itself, and sometimes that we can warning or alarm the battery that, okay, battery, because we are going to the eclipse modes, is it possible that the battery get the warning first, so the DOD is to decrease significantly? Like when we are in the geosatellites, we can say that Telkom 3S or Telkom 4, we have to do like the operational procedure. We have to check some things, and we have to do the procedural things that maintain the condition of the satellites, and also get the conditions of the battery and EPS. Okay, this is the eclipse. You're going to the eclipse, and this is the remarks, and we have to set the alarm.
Yeah, I think the idea is similar. In PCDU, we can implement the battery protection, as I mentioned, over voltage, undercurrent, and if all of those is to protect so that the battery will not degrade, or the capacity will not degrade significantly because of the battery failure. And when this certain threshold is reached, what the satellite should do, or the operator in this case should do, is to see how much, to analyze how much the power remain on the battery, and decide which of the component that you need to shut down if necessary. And this is not something that this is something that you need to plan during the preliminary design. This concept of operation, you need to define if this condition happen, which device has the priority to operate, which cannot be switched off, which is safe to be switched off. I think that's the answer.
Okay, and it will define in the preliminary design also, or maybe in the missions design documents. Yeah. Okay, and there is a questions from Pak Arifin Nugroho. It's just this is the clear questions that, do you think Indonesia can be one of the top list of nickel cadmium battery producer, as there are huge nickel deposits in the country? And what will be the challenge about producing lithium and lithium-polymer in Indonesia? Yeah, this is related to the nickel. Yeah, this is the hot issue.
I'm not sure. I cannot answer this. It's not an easy yes or no question. It's a lot of factor involved. I mean, we are a producer of raw material, but is there any? I mean, maybe Indonesia can, if it's in terms of technology, maybe we can achieve that to be a top list. But it will be back to the political will. Is this something that the government interested in?
Okay, but overall, nickel cadmium and Leon and also lithium polymer, they have a similar characteristic, isn't it?
Yeah, yes, it is.
Yeah, okay, so, okay. And this is maybe the second last question. Is there any difference battery regulator between equatorial and also inclinations orbit?
Battery regulation between equatorial and high inclination orbit. I think the difference on the battery regulation is not depend on whether you're putting your satellite in the equatorial or high inclination orbit. It's more on how you want to control the whole EPS system, your EPS system, and is it automatic or not, or how many views you want to use. It depends. Even the same equatorial orbit satellite might have a different approach in designing the PCDU or EPS.
Okay, and maybe this is the last question for me.
Yep.
About COTS module. So, is it running well, the COTS module power in Lapan? I mean, like, is it not well prepared actually? Is that well delivered to Lapan? And also, it has been testing and something like that, okay. Or is still in the design?
Yeah. The COTS module for the battery, as I present previously, it's already flight proven from the ABSL. It's flight proven in many satellite mission. However, in Lapan, we are not used for Lapan A1 up to Lapan A4. We are not using COTS based battery. We are using space grade battery. So in Lapan A5, we are. This is the first Lapan satellite that we are going to implement the COTS battery, and until now we still haven't procured the battery, so we cannot give we cannot review the performance based on our own experience.
Okay, thank you for the comprehensive presentations and well-defined answer in the questions and answer sections. I think that's all for the first and the second sections. And thank you very once again.
Thank you, Mr. Purwa, everyone, for the questions.
Thank you. And we are going to the third session or the last session. But in here, I'm moving forward to Ms. Edward that will guide us to Mr. Andri Pranata presentations. Mr. Andri is one of my outstanding partner when I was in TELKOMSAT, especially in satellite control operation. So I'll give the time to Mas Edward and Mas Andri. The time is yours.
Hello. Can you hear my voice?
Yes, Mas, clear.
Okay, thank you very much. But I believe I should give it back to the Mr. MC first, for giving certificate appreciation for our first and second keynote speech. Am I correct, Mr. Lutfi?
Yes, it is correct.
Okay.
Thank you, Mr. Edward, for giving me the chance. Thank you to Mrs. Desti Suryanti SSE and Mrs. Ray Fitrianingsih for delivering such an amazing presentations. And also thanks to Mr. Purwa Manggala that has been lead the first session and the second session. Next is we'll have certificate appreciations. Maybe operator can help to share the certificate. Yeah, once more. Thank you to Mrs. Desti Suryanti as the first speaker and Mr. Ray Fitrianingsih. Maybe we can next. And thank you to Mr. Ray Fitrianingsih to be the second speaker. Now let's dive into the last session, the third session, that will be moderated by Mr. Edward STMT. Maybe operator also can share TCV. All right. Mr. Edward is graduated from Telkom University, majoring telecommunication engineering in 2011. He also got his master degree from Bandung Institute of Technology in 2016. He also actively involved in several research, especially related to satellite. Maybe to the Honorable Mr. Edward, time is yours.
Thank you, Mr. Lutfi, for the time. Hello, everyone. My name is Edward, and I will be your guide for this last session in this workshop. So thank you very much for all participants for staying in this workshop. And we are going to another exciting session that will give you the insight about the power management in a spacecraft from our another expert today. So our expert in this last session will be from satellite industry. And here we already have Pak Andri Pranata from PT Telkomsat, one of the biggest satellite operator company in Indonesia. Okay, here's the CV of Mr. Andri Pranata. So he's a telecommunication engineer who graduated from Telkom University at 2013, and he was working at Huawei Tech Investment as a project manager from 2013 until 2015. Then he joined PT Telkomsat later on. He started his career as a spacecraft operator, and currently he is working as a spacecraft analyst. So let me greet Mr. Andri Pranata. Hello, Mr. Andri Pranata.
Hello, Mr. Edward. Can you hear my voice? Oh?
Yes, clear. How are you today?
Yeah, I'm doing good. Thanks for asking.
Okay. So without any further ado, Mr. Andri Pranata, time is yours.
Okay, thank you, Mr. Edward. Wait, I'm going to share my screen.
Okay.
Can you see my presentation slide right now?
Yes. Can you make it full screen?
Yes. Wait a sec.
Okay,
Is
it's
it full
already
screen
full
now?
screen.
Okay. So can I start the presentation? Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon all. Thank you, Mr. Edward. Thank you, people in the committee, Satcom Radar Laboratory of Telkom University, Nano-Satellite Division, LAPAN or BRIN, which I cannot mention one by one for the opportunity given to me to be one of the speakers at this workshop. So my name is Andri Pranata Kusuma. You can call me Andri, and I have worked as a spacecraft analyst at PT TELKOMSAT since 2020. It's been 2 years actually, and previously, like Mr. Purwa said, I worked with him as one of the spacecraft controllers at Telkom Satellite Division back then. So in this occasion, I will share my presentation material about the power management satellite application. But as a disclaimer, my material is mostly applied on the geo satellites, because basically TELKOMSAT doesn't yet have any NGSO satellites. So these satellites will mostly about the geo satellites. And basically, I divided this content of the presentation into 5. The first one, I will talk about the EPS overview, or EPS in general, but actually it has been mentioned by Ms. Eri, so I just add something to complete the presentation. And the second one is the EPS component used in geosatellites. And the third one would be the power operation and monitoring related to the EPS. And the fourth section is about the nominal and contingency procedure. And the last one is the fault detection, isolation, and recovery, or we know it as FDIR, that works in geosatellites. So the first one, I will talk about the EPS in general. Okay. So basically, the EPS stands for the electrical power subsystem, as mentioned by Ms. Eri before, and this subsystem is this EPS system works to provide the power to the satellite under various conditions in the satellite life phase, from a launch phase to the end of the satellite life. So the EPS has the following function in general. The first one is to convert solar energy into electrical power, and the second one storing the energy in the batteries, and the third one discharge or dispose or use the energy from the battery into the power state if the power state from the solar array is not enough. And the fourth one is the conditions, the energy for appropriate distribution to the satellites. And the last one is distribute the energy to spacecraft loads. So EPS provides power through all phases of the missions, including the sunlight operation, where the satellites is directly faced with the sun. And the second one is the eclipse operation, and the third one is orbit tracing operation. So this one is about the EPS overview in general. So basically, as we can see here, there is a solar array in our satellite. So this is the main equipment of the satellite where it gets the energy. So solar arrays gets the energy, and the energy or the current flows to the power conversion or power conditioning unit, and so it will be distributed to the spacecraft loads here, and it's also distribute the power into the battery if the battery isn't full charge enough. So so the battery will be fully charged. So as you can see here, where the battery is, where the battery color is red, it means that the battery will be used when it's on the eclipse operation, orbit racing, and whenever the solar array doesn't have any sufficient power condition. So this is basically the electrical power subsystem works in geosatellites. Basically, it is the same with the LEO satellites that have been mentioned by the other speakers before. So the first one is when the solar array, or SA here, is exposed to sunlight, the solar array becomes the current source. So as mentioned before, that the solar array consists of the photovoltaic component that will stores the energy from the satellite from the sun. And as you can see here in the graph, the current from the solar array will go through the shunt circuit, but basically it will flow directly. Then, as you can see here, there are two switches which connected to the batteries, and in nominal condition it is NO, or we can say it's normally open, because we use the solar array as our main source of the power. So when the battery is full charge, we don't need to use the batteries for the source of power. So as you can see here, the entire subsystem is considered as a load, where there are a lot of loads, like thermal subsystem, propulsion subsystem, ADCS, DHS or PCR, and many more. So when the load increases, the bus voltage will also increase. This additional load increase will be detected by this component, or VMC, the voltage monitoring comparator, and it will ask the shunt circuit to return some of the current from solar array back to solar array itself, and therefore the bus voltage is kept constant. And for your information, overall, the satellite subsystem in geosatellites operates at constant voltage, about 100 volt DC. So this one is about the solar intensity, and the first figure here is about the position of the sun in respect to the Earth periodically. And while the geosatellites is always in a fixed position at the equator. So as you can see here, on maybe sometimes around June 20, it is considered as a solstice season, and we will get another solstice season in December 22. It is a condition where the sun creates like 23.5 degrees above the satellite or below the satellites. And on June 20, we as an operator, we tend to know as summer solstice, and for the December 22 December, we can call it like the winter solstice. And for the equinox itself, or we can say like the eclipse season, there are two eclipse seasons in geosatellites, where it happened at September 23 and March 21. We call it, we as an operator call it like the March 21 as a vernal equinox, and the September one we call it as the autumnal equinox. So basically, like I said before, there are two eclipse seasons in the geosatellites. So each season consists like about approximately 45 days, and the duration itself might be different since the sun itself is moving, right? And it will be on its peak at September 23 and March 21, which it has actually it is a perpendicular position where these satellites will not get any sunlight. So the longest duration of the eclipse approximately around 70 minutes. And the following figure is an overview of the power received on the solar array in general on geosatellites. Each year actually will not be the same due to a satellite's nominal condition or natural conditions, but we will have characteristic similar to this following picture. On this graph one, the left one here is the distance factor of the sun, where you can see is in the blue graph here. This is the solar distance factor, and the red one should be the sun declination factor. Like I said earlier, like the degree or the angle of this of the sun would be different each time. So we normalize those graph, and there will be this final graph. We call it like the normalized sun intensity. So this graph tell us like whenever the point at this graph shows us the solar array solar power at that time. So basically on this graph, like we can see that here in March, we can see that the solar intensity is higher than the June one, because it is lower actually. And about the solar array, in geosatellites, solar array position needs to be always positioned in perpendicular position from the sunlight in order to produce maximum power. So as you can see here, this is the solar power variation over life. This is the theoretical assumption in geosatellites orbits. Like we said that usually geosatellites lifetime is about 15 to 16 years lifetime. So as you can see, the power fluctuation here in this part of the graph, we took a sample, like this is the September equinox, and this is this December solstice, and we will go back up again on March equinox, and it will be down again on June solstice. And what caused the power fluctuation, as you can see here, it is because simply because that the degradation of the solar cell itself. So the next one we'll talk about the sunlight operations from a satellite perspective. So during the sunlight condition, the satellite loads are powered directly from the solar array using the sun regulator system to provide the regulated voltage at the power bus. Basically, as I said before, that the solar array is the main source of the power whenever in the nominal condition. Like we don't need to use the battery in the nominal condition. So different from the sunlight operation, this is the equipped operation from the satellite perspective. Like I said earlier, that the geo satellites will approximately have like 70 minutes maximum on each season, and basically there are two kind of eclipse. As you can see here, let's imagine that this is the sun and this is the Earth, and let's say that this is our satellite here. So as a human, we can assume that that is the solar eclipse, right? But we as an operator tend to call it like the eclipse caused by Earth, or we can simply call it like Earth eclipse, because we are in this position here where we cannot get any solar power. And the difference is also we don't use solar array in eclipse operations. It doesn't it will not get any power, so we use the battery on every eclipse operations. So the second part of the presentation is the EPS component. So I will talk about the EPS component that used in geo satellites generally. So the first one is the solar array, or simply we call it SA wings. It is a two identical planar wings, or which is located in each side of the satellites, and the number of the panels depends on the mission requirement and the budget, of course, and it consists of gallium arsenide and silicon cells, which mentioned by Ms. Desti in the first presentation. And the second one is the solar array drive assembly, or motor. We as an operator call it SADA or SADM. It is a motor that moves the solar array counterwise or counterclockwise based on our requirement, and usually solar array rotates at full 1 revolution a day. And the solar array drive assembly itself has a function like to transmit power and to ground, basically to the ground the current, and the telemetry to transmit the telemetry across the rotating interface. The third one of the EPS component is batteries, which mentioned by Ms. Ari in the second presentation, like for the example, like the nickel hydrogen or NiH2 and lithium-ion batteries. The fourth component is PCU, or power conditioning unit, which have a function to perform the power regulation 100 voltage bus from the solar array and battery during solstice and eclipse operation. And the last one is the battery software management. So this is basically the function of the battery software management. The first one is to recharge batteries following the eclipses or discharge, any discharge. And the second one is to detect the end of the charge. And the third one is to maintain the battery state of charge during solstice. And the next one is controlling battery temperature in conjunction, or it works with a DHS or data handling subsystem or the thermal subsystem. The fifth one is supports safety monitors which prevent over discharge or over voltage protection or something. We will talk about that later. And the sixth one is the commendability, or we can say that the battery software management, since it's a software, so we can actually commence anything that related to the EPS. So this is the picture of the component, the EPS component I mentioned before. The first one here, as you can see, this is the solar array, one of the solar array that used in our previous satellites. And this one here is the solar array drive motor, where it can move the solar array automatically. And this one here is the pack of the lithium-ion batteries. And the last one here is the power conditioning unit, or we simply call it PCU. Okay, the third session is about the power operation and monitoring. And I've already mentioned it before, like this is the power generation during the sunlight. As you can see here, this is the block diagrams, and as you can see here, this is the north solar array part, and this is the south solar array part, which with its motor, and it can get the sun, and then the current itself will go to this power conditioning unit, and it will regulate the power about 100 voltage, and it will be distributed to all components in the satellite. Basically, this is one of the block diagram used in our satellites, and it is not applied to all of our satellites, but basically it is the same. Like this one, PFDIU stands for the platform, or where the powers will be distributed to all the equipments, and DPLDIU here stands for the payload. So the power itself will be differentiated to those components. And here, as you can see, in eclipse condition, we don't have enough sun power to operate all the equipment, so we use the battery. Then the battery itself, so we stop here. The PCU will not get any current from the solar array. So the current source or the voltage source will be from the batteries, and from the batteries it will still go to the PCU, and it will be regulated to all the satellites platform. So the subsystem basically is fully autonomous during the eclipse season. So like Mr. Purwa have mentioned earlier, that in our satellites, the satellites will detect that it is an eclipse season, or it is a solstice season, and it will do this procedure automatically. What I mean is switching the battery or the solar array when it needed. So as an operator, the telemetry that we monitor during the sunlight operation should be like this. This is the example of the telemetry that we monitor during the sunlight, like the solar array current, the satellite load current, the shunt current, the solar array position, battery voltage, or so on. And during the eclipse, we monitor also all of the sunlight operation telemetry, but with since we're using the battery as one of the one of the power source, we also monitor the battery discharge current, battery charge current. Maybe we can record this start time of the charging, stop time charging, start time discharging, or stop time discharging, and the depth of discharge itself. The section 4 here is about the nominal and contingency procedure regarding to the EPS. So as a disclaimer, not all satellites have the same procedure, especially when they are built by different manufacturers. This procedure here in this presentation do not apply to all of the TELKOMSAT satellites. So yeah, this is the general perspective of the nominal or contingency procedure. So the first one here is I will talk about the seasonal management. Since I mentioned a lot about the sunlight and eclipse operation. So this is basically the adjustment of the battery management software before and after eclipse. So this procedure is basically carried out to modify the charge or discharge parameters to suit the eclipse season and can be adjusted again during the solstice. It is basically to prevent the premature aging of the battery. So the next one is the solar array repositioning. I've seen in the question in the chat box previously, like and Miss Desti have already mentioned, like in Leo satellite, in their satellites, they need to contact, they need to have a coordination with their attitude control expert about this. But basically in GEO, we don't need to do that since we have this kind of motor, and basically the satellite itself is still moving on its orbit. So we just have to find a better angle for the solar array to see the sun. Basically, it is done when there is this kind of telemetry alarm, such as the comparison of the position of the solar array with the direction of the sun's position. So we have that in our satellites. The next one is the eclipse monitoring. Basically, like I mentioned earlier, that we need to record some telemetry, like I mentioned earlier, like the start of discharge, start and stop discharge, start and stop charging, or something like that. And we need to monitor that because we don't want to have like an over discharge or something. So we need to maintain those batteries in even though it's automatically done by the battery software management, but we need to carefully monitor that, since we don't want to have conditions where there will be another load decrease unexpectedly. So we need to have a load shedding that we'll talk about later. So the schedule itself comes from the orbital team, where there are teams who calculates the ephemeris data, and we as an operator will follow that that schedule. And basically the eclipse operations are time critical. So back in our previous satellites, it is very critical, but it's not for the battery, it's for satellite itself. It's just an intermezzo, but actually, like in our previous satellites, if the eclipse we forgot about the eclipse time, Like eclipse time consists like the start time of the penumbra itself, and it will be then after penumbra we will go to umbra phase, and then back to penumbra, and then we will get the sunlight again. So in our previous satellites, we still use like the Earth sensor. So whenever the sun comes to our Earth sensor, it will interrupt the Earth sensor. So if we don't do that at that time, our satellite will like twisting around on the orbit, and it's very dangerous. Just intermezzo. So this one is about lunar eclipse. So I mentioned earlier that we call the regular eclipse season as the Earth eclipse, since we are in the right position, and in the middle is the Earth, and the sun is on the other side of the Earth. So basically, lunar eclipse is the eclipse caused by moon, where actually the Earth will be on the right side, and the satellite itself will be on the middle, and there will be a lunar or moon, and the sun itself will be on the left side. So the moon itself will interrupt the sun acquisition. So it is not like a long duration like the regular eclipse season, since we cannot the moon itself is basically smaller than sun, right? And it is not that long, but it is become a concern where we have this kind of lunar eclipse inside the Earth eclipse. Like we actually, based on the prediction, we will have that kind of condition. So it is concerned that we don't want to have our spacecraft batteries. Basically, in every eclipse, we want to have like full battery charge on each cycle. So whenever comes an interruption like lunar eclipse, so it will interrupt the charge phase. So we are afraid that we cannot survive on the next eclipse cycles. So that's what we're afraid, and that's why lunar eclipse is also important to be monitored. And this one is battery capacity verification. As the procedure name itself is to verify the battery before entering the eclipse season by discharging the battery capacity to its lowest point. Ms. Eri also mentioned about the capabilities of the lithium-ion battery that can be discharged into zero, but will basically reduce the battery life. So we don't do that. We just want to decrease it at as low as possible, and charge the battery again. So the goal of this procedure is to basically collect or to trend the battery capacity degradation rate, and to assess the cell charge rate set points. And the schedule itself, like I said, it is before the eclipse. So on each year, usually there are 2 battery capacity verifications. And what I've mentioned earlier, that those are the nominal procedures that we use in geosatellites, and this one, the load shedding, is the contingency procedure. So this contingency procedure is called load shedding. Shedding means like remove some loads on the satellites. So this procedure is provided to address emergency load reductions that may be required if insufficient power from the solar array power or battery energy, or both, is available to support or sustain the spacecraft electrical load. So this situation is happen if the state of charge or SOC is reduced by 20%, before the next eclipse. That's why what I mentioned earlier, that if the lunar eclipse happen in the middle of the Earth eclipse, it can interrupt our charging phase of the battery. So there might be a need to do this load shedding procedure. So what will we do in this load shedding procedure? We just simply remove spacecraft loads by turning off or cycling the power as many units as practical or possible. Basically, we turn off the maybe like the unused payload or unused secondary equipment or something like that. But we might turn off the main equipment if the power required is not sufficient. And the last one, the last part of my presentation is about the failure detection and isolation and recovery, or we as operator call it the FDIR. So basically, the FDIR is the capability of the satellites to detect any failure which potentially leads to a satellite loss, a mission outage, and performance deterioration. And it is also function as an isolation, or like its name, and to recover a failure. Let's take a sample for maybe there are a failed satellite unit, or maybe something, and the FDIR itself will automatically swap to the backup configuration. And the FDIR guarantees the missions as far as the satellite integrity is not endangered, actually. And the fourth one, the mission itself can still be interrupted in some case of critical failures. So the FDIR itself can be interrupted by us, by ground, whenever it needed. So because we don't know what happened to the satellites up there, right? And there might be something that that is really critical that needs our interruption. So this is the EPS FDIR example. So the first one is the failed cell monitoring. So actually batteries consist of cells. And if one cell voltage is different, that's why we need to maintain the or monitor the cell voltage too, whenever in nominal or eclipse condition. So whenever there is one cell voltage is different than the others, so we need to bypass that cell, so it will not be used by the voltage acquisition function. The second one is the over voltage position. So in order to prevent the damaging of a cell, a battery over voltage protection, or OVP, indicates that the battery has a voltage above the maximum limit. So the FDIR itself will basically reset the configuration and force battery into pause mode. The next one is the over discharge protection. So this condition is where the discharge capacity is more than the permissible value for discharge. So the FDIR itself will check before starting to charge that the battery voltage is not too low. So the action itself, the FDIR action itself will resetting the battery configuration, force battery into charge mode, and turn off payload to conserve power. The last one is the low state of charge during nominal and loss of lock or LOL condition. So this condition is where there are any battery discharging, and the state of charge itself is, or the battery capacity itself is less than 12 ampere hour. In nominal, and in loss of lock, it will be needed about less than 40 ampere hour. So the action is simply load shedding, or payload mute or turn off if needed. The heater is also turn off and disable if needed. So basically, it is because that it has happened because like the loss of solar array pointing, and our engineer said that if the state of charge is about less than 10 ampere hour, it means that we will need around 10 minutes of it is about around 10 minutes of power available. So the load shed helps to extend power to about 1 hour, which means that we can have more time to recover or do contingency procedure. I think that's all of my presentation. I simply hope that it will give you insight about what geo operation looks like, and I would hope that this presentation can give you insight about your next project on the nano satellite or geo satellites. That's all. Thank you. Back to you, Mas Edward.
Okay, thank you very much, Mr. Andri. Wow. As I mentioned before, we here see another dimension of how we manage the satellite power generation. Yeah, and according to Andri's presentation, yeah, the architecture of nano-satellite and geostationary satellite power subsystem is relatively the same, yeah, but how to manage the power generation and how to face the situation, it seems like the geostationary satellite is more tough, yeah.
Yeah, kind of.
So thank you very much, and let's move to the discussion session. And we have two questions from, not two questions, two participants who already write down their question, but every participant wrote down about more than two questions already. Okay, let me read the first question from the Pak Efri Suartono. Yeah, he has three questions here. Yeah, first, is there any need for an external protection system other than already stated internal protection systems such as overcurrent or etc.? Any disturbances that occur for over voltage condition, excharge, and etc. So maybe you can answer the first question from Ms. Pak Efri.
Okay, so for question number one is there is basically it is still needed like the external protection system other than the already stated internal protection subsystem system by software. So on the hardware itself, like Miss Ari already mentioned, like we need to protect our battery from the extreme heat condition or extreme pressure above the Earth on the outer space. That is one of the passive protection or external protection system that applies to our batteries or our EPS system, and yeah, I think that's all because the battery itself is managed by another software called, maybe it's not applicable to all satellites, but in our one of our satellites have the lithium-ion management unit. So it is different than the battery software management itself, so that it can maybe this component can actually have its own protection to the battery. So I think that's answered the question.
Okay, is that software implemented on the satellite or on your ground station?
In the satellite, actually.
Oh, in the satellite.
Yes.
So alongside the protection, hardware protection, so you already you also plan software based protection, yeah?
Right.
Okay, let's move to the second question from Pak Efri. What about when the BSM battery software encounter a problem and you cannot fix it?
Yeah, actually, it's a good question, and Actually, there is a change or a possibility where the battery software cannot be fixed, right? There is a change. It has at least a probability, right? And whenever we can fix it, we can always try to do something. And like I said, there are many things that can cause the battery software problem. So we can it's not simple actually, but actually we can try to reconfigure the battery software by resetting the software or something. And since the satellite itself has a processor, so we will try to reset the processor if needed. So so that we can find the actual so that in hopes that the software management gets it the problem itself is clear. So if we can also use that, we don't have to rely on the battery software. So there is also capabilities of the satellite where we just can send a simple single critical command to the satellites. So we don't have to rely to the battery software management. So we just have to send the command needed to conserve power, something like that.
Okay. Will it affect the operational daily operational of your satellite?
Of course. Let's say if say that we have problems in our battery software management where it cannot define the end of charge, let's say. So the battery itself will be charged over time. So as mentioned earlier by Ms. Ari and Ms. Desti, that if the lithium-ion battery gets charged, it will premature the battery life. So we need if that things happen, we need to stop the charge and let the battery drain itself for a bit, then charge again. And it will be a hard work to do for the operators.
Oh, okay. It's so intense, yeah.
Right.
I think you have to stay for 24 hours every day.
24/7, right?
Okay. So thank you. Let's move to the next question. What is the difference in the output power characteristic of PLPS? I think it's a solar-based grid, yeah, on the ground, yeah, with the satellite orbit.
Yeah. Actually, I personally, to be honest, I don't know a thing about the power generation, solar power generation in ground. But what I heard from Miss Ari, and I read a literature about the component that used in the satellites should be space graded or space qualified. So that is the difference of the operation. Maybe I don't know what equipment that used in the solar generation in the ground, but it is simply that the satellites use the component that is been tested for space qualified qualification. I think that's
okay.
it.
Yeah, I agree. There must be a difference, at least from the type of material. Yeah, because the solar cell on space will have possibility to experience harmful moments here.
Right.
Yeah. Okay. Thank you. That's from Mr. Every, and it's the last question from Fasni. Yes, for questions here. Hopefully you can answer all of his question. Okay, first, is there any risk from repositioning the solar array position, and how to mitigate the risk?
Of course, there are risks when we reposition the solar array. Like since we are using a motor, right? We're basically using a motor to rotate the solar array. So there will be a change where the solar array itself cannot be rotated, and to mitigate itself, like there are basically a component in the solar array drive which works like a redundancy, so it will prevent those things to happen. So like I said earlier, that whenever it can also be cannot be recovered too, it has a change, it has a possibility, and when that things happen, that it will be bad for our satellites. So we might have just one solar array that works, so that it will decrease our power margin to operate the satellites.
Oh, okay. About the motor itself, is it 2-axis or 3-axis motor?
Actually, it's basically a motor that moves like I don't know what it called, like it moves like clockwise or counterclockwise.
Okay.
It's just like a motor. Yeah,
One
something like
axis
that.
maybe, yeah.
Yeah.
Only one axis.
Yes, only one axis. Yes, you can say that.
Okay,
Right.
okay. And it's synchronous between both wings, yeah.
Yes, it should be identical position on both sides.
Okay. Thank you. And let's move to the second question. What does the operator need to prepare when spacecraft encounter lunar eclipse right after the Earth eclipse? Wow, it's like a double kill, yeah.
Yes, it's a good question actually. What operator needs is it is different actually in each satellites, but here in our latest satellites we can actually predict. We can actually predict, since lunar eclipse prediction is given by our manufacturer. So we can they can predict that there will be this lunar eclipse. You will face this lunar eclipses in this time of your satellite lifetime or something like that. So we need to prepare about that based on the duration of the lunar eclipse itself, and compared with the actual power remaining on the satellites. So we have that kind of procedure, and whenever the power isn't, like I said, if the power isn't sufficient enough to operate the satellites, I think we should do like the power or load shedding, and that's before the eclipse happen, so that the power itself will not be degraded too much.
Okay. How long do you do the preparation? Is it a week before or a month before the event?
It should be as close as possible to the predicted eclipse schedule. Like we don't have to do it like 1 day before or 1 night before. No, that's too close. But since the power of the satellites is not constant, but we can predict actually, since it will not have a very significant fluctuation, right? But we can say like we can prepare like 3 days or 4 days before that lunar eclipse happen.
Oh, okay. Thank you for your answer. Okay, next, the third question. When the VSAT, I think it's the voltage set, yeah, needs to be adjusted after each of battery capacity verification.
Yes, actually, it is not a common things to do in our current configuration, but it is still needed sometimes around whenever we see that the charge rate or the charge rate of the battery cannot be 100% in 1 day. So this battery capacity verification, like I said before, is basically we decrease our battery capacity to almost zero and recharge it again, and we just want to see that from the lowest condition, lowest capacity condition, how long that the battery will get 100% condition. So if on that position, if on that condition that the capacity get back 100% more than a day, I think it will need a voltage set update or something like that.
Is it different with the calibration things on your satellite?
Actually, it's basically the same, but we don't calibrate it. If this VSAT need to be adjusted, I think it is called calibrated, but calibration. But basically, it's just we just want to see the trend actually.
Okay. So yeah, it's the last question. Do the operator just rely on FDIR if there are any failure on specific EPS, or when does the operator need to interrupt the FDIR process?
Yes, I get what the question means. So basically, every manufacturer said that you don't have to do anything on your satellites, and let the FDIR do the things for you. But they still recommends us to monitor the FDIR itself, since FDIR itself is a pack of algorithm that will change anything if there's any failure or something, like I mentioned earlier. So whenever the configuration is doesn't meet our requirement, so we need an interruption from the ground or from the operator. So so the answer basically is we cannot rely on the FDIR, only the FDIR. So we need our monitoring also, and our interruption itself for the failure.
Okay. So the operators still have important task here to to maintain the battery operation. And
right.
Have you experienced any human error when you are monitoring your EPS?
Actually, yeah, and it was not about the EPS. It was not, it was regarding the other subsystem, and it is proven that it is still the operator action to deal with those kind of error, since let's say that this FDIR, if there is a component, one component is error, it will switch back to the configuration to the backup configuration, right? And let's say in this backup configuration, the anomaly happens again or something like that. So the satellite will not have any other backup configuration. So that's why the role of the operator itself is important. Like, we need to analyze, is this first equipment that malfunction or error before is really destroyed or really broken or something. So we need to analyze that. If in satellites we know a single event upset, or maybe maybe it was a bit error that caused the FDIR to be activated. So if the result of our analysis is the first component is okay, so we just have to switch it back to the first equipment. So, I think that's answered the question.
Okay, thank you very much. Oh, we have another question from Pak Arifin Nugroho. Okay, let me read the last question for this discussion session. From the industrial perspective, how do you compare lithium-ion and lithium-polymer in contesting the one against another for satellite application? And then for the high-throughput satellite application, what will be the chance of applying the most suitable of those technologies?
Okay, so actually, Miss Eri have mentioned about this, and basically, in contesting contesting the one against for another satellite application is lithium polymer is also, based on what I heard, based on what I heard, lithium polymer is also used in the satellite application, and based on the literature that I've read is in compares to the lithium ion, the lithium-ion is offering the a large capacity at the low price, and the lithium polymer itself, life cycle itself is also shorter, and I don't know that the battery store less energy than the same size with the lithium-ion. Ms. Andri talked about this previously, and in the current project of TELKOMSAT, we actually are developing a new satellite, and it is HTS satellite, the high throughput satellite, and the battery that recommended for us to use on that project is lithium-ion too. So yeah,
like lithium-ion still with the game, yeah.
Yeah, for now. And as I talked about earlier, I personally experienced having satellites with another kind of battery cells, not only lithium-ion but also nickel hydrogen. It was on our previous Telkom 2 satellites, and yeah, it has a different characteristic. So I think lithium-ion is, in my opinion, it's just my opinion. It is better, and based on what our manufacturer said, that the lithium-ion tends to have a longer life cycle or something like that.
Okay, thank you for your explanation. And yeah, we have it's like we have a good time here in this workshop. Thank you very much, Mr. Andri Pranata, for your presentation and discussion.
Thank you, Mr. Edward.
Yeah. Okay. I think it's the end of the third session for this workshop. So before it's coming to the closing, I will give back the session to the Mr. MC, Mr. Lutfi.
Thank you, Mr. Edward. First, thank you to Mr. Andri Pranata for giving a great explanation about power management satellite applications. And also, thank you to Mr. Edward for leading the last session. The operator may help to share screen the certificate. All right. Once more, thank you, Mr. Andri Pranata, for sharing in this occasion.
Thank you, Mas Lutfi.
Okay. Ladies and gentlemen, we now come up to the end of our workshop. We would like to thank to all our partners and collaborators. Of course, our heartfelt thanks to each and every one of you for joining this event. And don't forget to fill the attendance form. The link will be provided in the Zoom chat, because we'll close the form at 1:30 p.m. And now this one of agenda that waited for most of us is the announcement for the best 3 questions in this workshop. Right, congratulations to Mr. Ahmad Fahrijar Ramadan and Mr. Twi Rahmat Mulya, and congratulations to Mr. Fasni Rafsanzani. The reward will be, we will contact you by email, and so don't forget to fill in the attendance form. Right. I think we come up to the end of this workshop. On behalf of the committee, I'm Lutfi Nur Syadi Jamashari as MC. Apologize profusely if there are mistakes or shortcomings in today's event. Lastly, thank you for joining us and have a great rest of your weekend. See you in the next workshop. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih. Thank you.
Thank you, Mas Andri. Terima kasih. Terima kasih, Bu Eri.
Thank you. Thank you, Mas Lutfi.
Terima kasih, Pak Arifin juga. Terima kasih banyak.
Thank you, Mas Edu.
Terima kasih, Pak Arifin. Thank you very much.
Thank you, Mbak Kania.
kasih Pak Arifin, teman-teman semua. Mohon izin.
Terima kasih
Terima
Bu
kasih.
Eri atas kedatangannya, Bu Eri, Desti. Sampai jumpa.
Very, terima kasih. Desti, terima kasih. Mas Andri, terima kasih. Mas
Terima kasih.
Pak Muhayyadi, terima kasih.
Pak Muhayyadi.
Pak Muhayyadi, terima kasih.
Terima
Pak
kasih banyak
Muhayyadi.
Pak.
Ya.
Mbak Kanya,
Selamat
terima
ya,
kasih.
sudah sukses perjalanan.
Luar
Alhamdulillah,
biasa. Atas bimbingan Pak Muhayyadi, terima kasih.
Terima kasih banyak, Pak.
Terima kasih banyak Pak.
Terima kasih atas dukungannya semuanya,
Baik.
organisasi maupun personal, luar biasa. Luar biasa.
Terima kasih Pak Arifin. Kita masih
Iya.
ada beberapa workshop lagi, Pak.
Iya,
Upcoming
iya.
PR, Pak.
Iya.
Kalau Senin kita
Insya
koordinasi.
Allah, insya Allah. Ini saya tadi udah minta sama Mbak Kanya itu apa namanya, bahan-bahannya,
Siap.
bahan presentasinya bisa
Oh iya.
diambil,
Ya,
bisa
baik Pak. Nanti akan dikirimkan melalui link Google Drive karena akan disatukan semua pembicaranya.
Oke. Saya juga saya berkewajiban melaporkan di tools dari IEEE, Mbak. Jadi harus ada judul yang pasnya apa, namanya siapa, kayak gitu.
Baik Pak.
Oh iya,
Nanti
Pak.
akan segera disidangkan.
Juga minta izin untuk melaporkan kegiatan yang sama di Toolsnya GRSS Chapter dan student branch-nya Tell You ya, Pak.